Okay, so number 3, part of the assignment here is 4.4, Calculus 30. A rectangle has a perimeter of 100 centimeters. Okay, so stop right there. Stop right there. You too, stop right. Okay. You guys looked up to me like, you're talking to me? A rectangle, perimeter. Okay, so rectangle, two-dimensional rectangle. That means that the length and the width, they could be equal, but they might not be equal. So a square is a rectangle. So they could be, all sides could be equal. We don't know yet. The perimeter is 100. So that means that if we had, let's say width here and length, then 2 times the width plus 2 times the length is 100. Okay? So packed in this question right here, the first sentence is a lot of information that we need to take careful note of, right? We have a rectangle. That's the general shape. We have a perimeter that is 100. So we've got a relationship between the variables. We have some information about how those variables are related. So what is the length and the width? What length and width should it have so that its area is a maximum? All right, so there's the second piece of these questions. We're trying to optimize the area. So what is the area of this rectangle? Length times width, right? Or width times length, yes. No, okay, that's great. So this is the one that I'm going to do calculus on, the area. But I have to try to make sure that we have, in all these examples, you want to make sure you have one variable and not 2, right? So is there a way that I could use the other information that I've given, like this over here, to isolate one variable and write it in terms of just the other one? Sure. You could isolate. It doesn't matter which one either, right? Which one do you want to use? Do you want to isolate L or W? Does it matter?
W. Let's go W.
You want to isolate W? Okay. So this is going to be 100 minus 2L. W is going to be 50 minus L. That make sense? So now I go over and I use this fact to say I'm going to write an area function in terms of L only. Because I've got L multiplied by what is W? W is 50 minus L over here. It's amazing, isn't it? So at this point, you can do calculus now. Or you might want to simplify this function now. You might want to simplify it so that you don't have to do product rule. Because at this point, you're going to do product rule. So let's not do that. All right? Let's do this, and let's say 50L minus L squared. How about that? That's really easy to take the derivative of now, right? Okay, going to speed up just a little bit here. So A prime of L is 50 minus 2L. Is that agreed? I want to let that equal 0 because I want to find the critical numbers. Because again, if I'm trying to optimize something, I want to know where a local max or min is going to be, and that's the number that I'm going to be focused on. And so this is going to be, what, 2L equals 50. L is 25. Okay? Now, is there 2 possible answers? Did I take the square root of anything? No. So just, even if there was a negative version, we would reject that, right? Because we don't want a negative distance or a negative dimension. So am I done? No. Okay. What does the question ask? Let's see. What length, and width should it have so that its area is maximum? I've got length. How do I find the width given the length? Right here. Yeah, I put it into what W is expressed as in terms of L. So W actually is 50 minus 25. The width is 25. So actually, this rectangle, when the area is a maximum, is when this rectangle is a square of 25. Now we found that out. And so you would write the sentence, the length and width should both be 25 and centimeters. Okay, so I'll write that out right here. The length and width should be 25 centimeters. Okay? You would write a little more legibly than me. Okay, any questions about that? Are we good? Okay. Now, here's just a hint. This won't happen every time. But if we're trying, and I mentioned this the other day, if you're trying to maximize the area, well, no, don't make it a square, but just have in your mind that, you know what, something as close to a square as possible is going to give you the maximum area for that kind of shape, for a rectangle. So that will come up a few times, just heads up, just the way it is. There'll be other questions, say maximize, what's the maximum volume, so it's a little bit different, but it's, with the dimensions themselves are pretty close to each other, that's where you're going to have some kind of maximum area or volume or something like that. So just keep in mind. Because this, if it was like this right here, let's say it was 2 units wide, right? So 2, that's 4. So that's what, 96? That's 48. Okay? So if we had this going on, what's 2 times 48? Is that going to be larger or smaller than 25 times 25? Right? Much smaller. Right? So we've got 625 units cubed squared here, and we've only got 96 units squared here. So closest to a square is going to be your maximum area. So keep that just under your hat.
Yes.
All right, number 6. A box with an open top is to be constructed from a square piece of cardboard. So envision this, a perfectly square piece of cardboard like this, and we're going to make a box like this out of it. How do we do that? Well, the piece of cardboard is 3 meters wide, and we're going to do that by cutting out a square from each of the 4 corners. So that's why they have these little perforation sort of marks here. This square is going to be cut out. Now, obviously, we would have a different size box if we cut out a larger or smaller square, right? So we don't know what the dimensions of this little square are. Find the largest volume that such a box can have. Okay. So that's the key, is find the largest volume. So if we cut out big chunks like I just drew here, right? We're going to have, if we cut out big chunks like this, we're going to have a pretty small base, and it's going to have quite a large height. If I cut out just a little bit, so like the tiniest little square, like this, right? Then it's going to have a very large base, but only a very small height. And that's not going to be the largest volume either. So we want to know where the sweet spot is. Okay? So bottom line is, we need to figure out what is needing to be optimized. So what are we trying to optimize? Volume. Okay? So volume equals length times width times height. If this is length, this is width, and this is height. That's 3 variables. It's a bit of a problem. We need to try and figure out how we can make this a function in terms of 1 variable only. So what other information are we given? Well, this starts off to be, what, 3 meters, right? And we don't know the dimension, okay, because that's actually what the question is being asked for. Cutting out a square of each 4 corners. It's actually asking for the volume, but we don't know what this dimension is, right? That's an unknown size of that square, so we don't know what that x is. So we have to have something going on here, and this will all make sense in a bit. So how can I use this right here to show what the, let's say, the length and the width of this box is? 3 minus x. Okay, you're getting close. This right here, from here to here, is actually 3 minus 2x. So one of these is 3 minus 2x. What's the other side? Well, it is a square piece of cardboard. So guess what this length is as well? It's 3 minus 2x as well. And that's, again, this and this. Okay? So is everyone following there? All right? So that's, and now what is the height of the box? X. Yes. Look at, here is the height, right? If you were actually to take that and fold it up, x would be the height. Wow. So by looking at all this other information, you see, what we've done is we've expressed each of the 3 dimensions in terms of x. So now we just need to write the volume, and we can write it as a function of x now. Length is 3 minus 2x. Width is the same. So it's really 3 minus 2x squared times the height, which is x. Okay, so that's half the question right there. Okay, what are we trying to maximize or optimize? Volume, okay, write out the volume. How can I change all of those variables into expressions with respect to just one variable? And that's what we've done so far. Now, it would probably be a good idea to, oh wait, do I have that number 6 already copied out? Oh yeah, it's already done there too. Ooh, nice. Okay, so it would be a good idea to maybe rewrite this volume without the product and the, because we're going to have to do product rule and chain rule and everything like that. So you can do that. But what else could you do? You could expand this binomial, this square, pretty easily and multiply everything by x. You could do that. So it's up to you. Again, product, chain rule, you could do that. Or you could just say, okay, if this is squared, that's going to be 9 minus 12x plus 4x, and then times x, which is actually going to be, sorry, there's going to be a square there somewhere. Squared. So this is going to be 9x minus 12x squared plus 4x cubed. If I did that right in my head. You guys agree with that? Yeah, you okay with that? So now you can do the derivative, and I'm going to let you guys take it from here, because I've done most of the work. So you guys take it from here and come up with the largest volume. Again, we're looking for the volume. So when you find x, right, you want to use that x to find the actual volume. So take a minute to finish this question. Okay, so as you work through this here, this is what you should get right here for the derivative. Okay, the 3 out there doesn't matter. There's no x, so there's no critical number associated with that. The critical number here would be 1/2. The critical number here would be 3/2. Now, we reject this one. Why? Because if we look just up here to the right, okay, remember, these are lengths, right? 3/2. So if I have 3 meters and I subtract 1.5 from both sides, that's going to give me an overall length of the box of 0. So that's no good. That would represent sort of a minimum, wouldn't it? So we don't want a minimum, we want a maximum. So then you use the 0.5 and, whoa. So then you plug your 0.5 in to the original volume function, and then this is 9 times 1/2. So you should get a volume of 2 cubic meters. That would be the maximum volume.
Is that to your whole answer?
Well, the question asks for what is the maximum volume that you can get out of this, and your maximum volume would be 2 cubic centimeters, yeah. If it asked for the dimensions, then what you'd have to do, we're rejecting this one, so you take 1/2, right, if it asked for the dimensions, and then you would put 1/2 in for x, in for each of these, and you could figure out the dimension. So the dimension's 1/2 here, the dimension here is 2, dimension here is 2. So it's 2 by 2 by 1/2. Those are the dimensions of that box. Got it? Yes?
I get the x for